Okay, welcome back. Excuse me. Now what I want to look at is motor characteristics, okay? Motor characteristics, direct current motors. Now, the interesting thing here is to look at how DC motors operate and the type of wiring connections we have in regards to DC motors. Okay? DC motors are divided into three classes, designated according to the method of connecting the armature and the field windings as shunt, series, and compound wound. Okay? So what I want to look at first is shunt wound motors. This type of motor runs practically constant speed regardless of the load. It is the type generally used in commercial practice and is usually recommended where starting conditions are not usually severe. That word should be severe. Okay? Speed of the shunt wound motors may be regulated in two ways. First, by inserting resistance in the series with the armature, thus the decrease in speed, and second, by inserting resistance in the field circuit. In the field circuit, the speed will vary with each change in load. In the latter, the speed is practically constant for any setting of the controller. This latter is the most generally used for adjustable speed service, as in the case of machine tools. And here we have a diagram, okay, showing you the shunt motor is able to operate with RPM control while it is at high speed. Okay. And here we have series wound DC motors. This type of motor speed varies automatically with the load, increasing as the load decreases. Use of series motor is generally limited to case where a heavy power demand is necessary to bring the machine up to speed, as in the case of certain elevator and hoist installations for steel chairs, etc. Okay. Now, series wound motors should never be used where the motor can be started without load, since they will race to a dangerous degree. Okay. Here we have series motor. Okay. The series motor is capable of starting with a very large load attached, such as lifting applications. Okay, so here's where we would use the series motors for lift shafts. So to lift the lift from one place to another, taking you to various floors. Compound wound DC motors, a combination of the shunt wound and series wound types, combines the characteristics of both. Characteristics may be varied by varying the combination of the two windings. These motors are generally used where severe starting conditions are met and constant speed is required at the same time. Okay, and here's a picture showing you the various types. Okay, now remember, these diagrams you should be drawing out for yourselves so you're familiar with the wiring system on them. Okay, the compound motor, a combination of the series motor and the shunt motor, is able to start with fairly large loads and have some RPM control at higher speeds. AC motors, squirrel cage induction motors, the most simple and reliable of all electric motors. Essentially a constant speed machine which is adaptable for users under all but the most severe starting conditions. Requires little attention as there are no commutator or slip rings, yet operates with good efficiency. Now, wound rotor slip rings induction motor used for constant speed service requiring a heavier starting torque than is obtainable with squirrel cage type. Because of its lower starting current, this type is frequently used instead of the squirrel cage type in larger sizes. Okay. These motors are also used for varying speed service. Speed varies with this load. So that they should not be used where constant speed at each adjustment is required, as for machine tools. Right, single phase induction motor. This motor is used mostly in small sizes where polyphase, meaning three-phase motors, polyphase current is not available. Characteristics are not as good as the polyphase motor, and for size larger than 10 horsepower, the line disturbance is likely to be objectionable, meaning that it will give problem with the line, might cause an imbalance in the line load. Okay, these motors are commonly used for flight starting and for running loads up to 1/3 horsepower. Capacitor and repulsion types provide greater torque and are built in sizes up to 10 horsepower. Now, synchronous motors run at constant speed, fixed by frequency of the system, require direct current for excitation, and have low starting torque. For large motor generators, such frequency changes, air compressors, and similar apparatus which permits starting under a light load for which they are generally used. These motors are used with considerable advantage, particularly on large power systems, because of their inherent ability to improve the power factor of the system. Synchronous motor speed. There are two ways to define motor speed. First is synchronous speed. The synchronous speed of an AC motor is the speed of the stator's magnetic field rotation. This is the motor's theoretical speed since the rotor will always turn at a slightly slower rate. The other way motor speed is measured is called actual speed. This is the speed at which the shaft rotates. Now the nameplate of most AC motors lists the actual motor speed rather than the synchronous speed. Standard AC induction motors depend on the rotor trine, but never quite succeeding to catch up with the stator's magnetic field. The difference in the speed of the rotor and the synchronous speed of the stator's rotating magnetic field is called the slip. Different motor designs will produce different amounts of slip. AC motors are designed with various numbers of magnetic poles. Standard motors have 2, 4, 6, or 8 poles. These poles play an important role in determining the synchronized speed of an AC motor. A motor's synchronous speed can be computed using this formula. Synchronous speed equals 120 times the operating frequency divided by the number of poles. So here, for example, a 6-pole motor synchronous speed is 120 times 60 equals 7,200 divided by 6, or 1,200 revs per minute. Okay. Now there's another way, of course, to calculate that, but I'm just dealing with one for the moment. Okay. You can apply the others for yourselves, and you can look those up for yourselves and apply them for your individual case. 4-pole motor synchronous speed will be 1,800 revs per minute. Use this formula to determine other speed pole relationships. Okay, I will leave that to you, and that will be the formula you'll be looking at. Now that's just one formula, because remember, you're looking at P equals, all you have a number of poles, P equals pairs of poles. So if I've got 6 poles, that means I have got 3 pairs. If I've got 8 poles, then it means I have got 4 pairs of poles. Okay, and that's just to show you a synchronous motor running, basically. And then I pick this up off the internet. I hope that this comes out quite clear. Let me go in a little bit, see if I can get it, make sure we get all the details in. Okay, and then let me come out a little bit. And here we have construction of a shunt wound DC motor. The design of a DC shunt motor is similar to other DC motors as shown in the following illustration, and that's your illustration here. Okay, basically. All right, so I'm just gonna make sure that we get that all in. Okay, and I'll move in a bit now, bringing that back into screen. Okay, and that will be it, I think. Hope you found this useful. Have a good day. Bye bye for now. Thank you.